All right, welcome. Today, we're going to break down the absolute core of programming, and we'll be using Java as our guide. Seriously, by the end of this, you'll get the essential concepts that every single program is built on. So let's dive in. So I want you to think about building something complex, like a big Lego castle. Before you can even think about building the whole thing, you have to know your bricks, right? The little 2x4s, the flat pieces, all of it. Well, programming is exactly like that. So the big question is, what are those fundamental Lego bricks of code? Okay, so we're starting right at the very beginning. Think of this as the raw materials, the stuff you need before you can build anything at all. We're talking about the containers for our data and the basic tools we use to work with it. And this right here is a perfect example of a super important rule in programming. On the left, you see a whole number, 100, and it fits perfectly into what's called a long variable, no problem. But now, look at the right. We try to put a number with a decimal in that same type of container, and bam, Java freaks out. It gives you an error. And why? Well, it's pretty simple. You're trying to shove the wrong shape of peg into the wrong hole. You've got the wrong kind of data for that box. And that brings us neatly to this concept of a data type. You can think of it as a rule book that's attached to every single piece of data in your program. It tells the computer what the data is. Is it a number? Is it text? And just as importantly, what you're allowed to do with it. This is the system that keeps things sane and prevents you from, say, trying to divide your name by your age. It just wouldn't make sense, right? So out of the box, Java gives us 8 of these fundamental types. They're called primitive data types. And as you can see, they cover the basics. We've got a set for whole numbers of various sizes, a couple for decimal numbers, one for simple true or false values, that's a Boolean, and another, char, for single text characters. These 8 are really the foundation for handling pretty much any basic piece of information you can imagine. All right, so we've got our data stored in these neat little typed variables, but just storing it is only half the battle, right? We need to do things with it, and that's where expressions come into play. An expression is really just any bit of code that computes a value. It could be something simple like x plus 10, or a logical question like, is age greater than 21? Okay, now pay close attention to this one, because this is probably one of the most common mistakes that trips up new programmers. Seriously, a single equal sign means a sign. It's the action of putting a value into a variable. Think of it as put this in the box. But a double equal sign means compare. It's asking a question. Hey, are these two things the same? Getting these two mixed up, oh man, it will cause you some headaches with bugs that are super confusing to track down. All right, we've got our data and we know how to do some basic operations on it. Now, let's give our program a brain. This next part is all about letting our code evaluate situations and make decisions. It's how we create different paths for the program to follow depending on what's happening. And the most fundamental tool for that is the if-else statement. It's so simple, but it's incredibly powerful. You just ask a true or false question. If the answer is true, the code goes down one path and does one thing. If the answer is false, it goes down a completely different path and does something else. That's it. This is the core of how programs can seem smart and adaptive. But what happens when you need to check one variable against a whole bunch of different possible values? I mean, you could write a giant, ugly chain of if, else if, else if, or you could use something much cleaner, a switch statement. Look how cool this is. It lets you group cases. So for example, instead of writing a separate rule for April and another for June and another for September, we just lump them all together and say, if it's any of these, the result is 30 days. So much cleaner, right? Way more efficient to read. So we've got our data and we've got our logic. Awesome. But a single variable on its own is, well, it's only so useful. Most real-world programs are dealing with collections of things, right? A list of all your contacts, a catalog of products in a store. We need good ways to organize and manage big groups of data. Our first tool for that is the array. The best way to think of an array is like a bookshelf with a fixed number of slots. When you build the bookshelf, you decide, okay, this will have 10 slots, and that's it. It can't grow or shrink, and all the slots have to hold the same type of thing. It's really fast and efficient, but yeah, that fixed size is its biggest weakness. And that limitation brings us to its super flexible cousin, the array list. If an array is that fixed bookshelf, an array list is more like an expandable bin. You can just keep tossing things in and it'll grow as needed, or you can take things out and it'll shrink. It's incredibly convenient. Just a small thing to notice here. With an array, you check its size with .length, but with an array list, you use a method called .size, a subtle but important difference. Okay, now for a classic gotcha that catches everyone, and I mean everyone. Look at this line of code. We have one list, mylist A, and we say mylist B equals mylist A. So, what do you think just happened? Did we just make a nice clean copy of the list? The answer is nope, not at all. And this is so important to understand. You didn't create a second list. All you did was create a second name tag, mylist_b, that points to the exact same list that's sitting in the computer's memory. This means if you change the list using the name mylist_b, you'll see those exact same changes when you look at mylist_a. They aren't two lists, they're two names for one list. So what does that mean for us? It means that if you actually want a true, separate, independent copy of your list, you can't just use the equal sign. That only copies the name tag. You have to explicitly tell Java to clone the list. See the code on the right? That clone method is what actually creates a brand new list in memory, totally separate from the original. This is how you avoid those weird, unexpected side effects. Okay, this next part is where everything we've learned really comes together. It's the most powerful concept of all. So far, we've only been using Java's built-in data types, for numbers and text. But what if you want to represent something more complex from the real world, like a user profile or a product in an online store or a bank account? For that, we need to create our own data types. And the way we do that in Java is by creating a class. A class is nothing more than a blueprint. It's a template. For instance, we could create a member class. That blueprint would say, okay, every single member we ever create must have a spot for a name and the spot for an age. It also defines what a member can do, like maybe it has a behavior for introducing itself. Now, the blueprint itself is just the plan, right? It doesn't hold any actual data. To use it, we have to build something from that plan. We have to create an object. You'll also hear it called an instance. This line of code here does exactly that. It takes our member blueprint, uses the new keyword to bring it to life, and constructs an actual member object in memory, filling it with the real data, Leonardo, and the age 21. And here it is. This is the moment it all clicks together. Look how we combine all our tools. First, we use our custom member blueprint to create individual objects, like Leo. Then, we create one of those flexible array lists, but we tell it that it can only hold member objects. And finally, we take the custom object we built and add it to our list. This right here is the fundamental pattern for building just about any complex, organized application. And there you have it. Think about the journey we just took. We started with the absolute simplest thing, a single piece of data in a variable, and we built all the way up. We learned how to make decisions, how to manage entire collections of data, and even how to design our own custom data types from scratch. You now have the complete set of fundamental building blocks. And here's the crazy part. Every single piece of software out there, from the simplest mobile game to a massive, complex system running a bank, is built from these exact same fundamental bricks. The only difference is the creativity and the complexity of how they're all put together. So that leaves just one question. Now that you have the bricks, what are you going to build?